Right. So yeah, we are done with the squeezing of a light source, right? Of quantum description. Okay. So what we'll do, we'll touch some what I mean uh, the sensors, solid state sensors. Now, if you see, you understand what I mean, the squeezing of light. Okay. You see, current light source. Okay, you see the light source is blurred, okay, amplitude wise as well as phase wise equally, right? Amplitude wise, see, amplitude is also blurred and phase is also blurred. Okay, if I have phase got squeezed, means phase is error wise reduced, amplitude can have more error. You see, the errors in amplitude wise is more, but phase is more accurate. Okay, right? So that is a phase squeezed, or I can have amplitude squeezed, means error in the amplitude is less, more accuracy there, but phase can be any value. So that is what amplitude squeezed state would look like for an electromagnetic wave. Let's say vacuum state in the sense no photons are there. So in that case, I see it's like a constant. Okay, right, fine. So a squeezed vacuum state. I can squeeze the vacuum state. Okay, right. Remember, even in the vacuum state, even no vacuum state also, it has some energy, which is h omega naught. That is called a 0 point energy. So in that case, I can still do the squeezing. Okay. So now I would see you people understand what is meant by squeezing. Okay. Right. Now let's get back solid state sensors case. Gravimetries, I will just go. Okay. Let me go to gravimetry. So where is that? Quantum sensors, huh? 1 minute. Let me open that. Okay. One minute. Yeah. We touched few things earlier. Diamond NV central base sensing we touched. Okay. And right. Yes, gravimetry we want to discuss. Okay. So it's a lot of text is there. Don't worry. I'll explain what I meant. Okay. So as you can see, right? As you can see, gravimetry, quantum gravimetry deals with the measurement of the gravity. Okay. Wherein the gravity known as a universal force of attraction acting between any two objects having some masses. Okay, right? So it's an obvious thing. G is, okay. Let me write down. Universal gravitational force is equal to, okay, G capital gravitational universal constant G multiplied by mass of m1 and m2 divided by this distance between m1 and m2 and acts along the direction of the connecting radius or connecting distance between. This is a gravitational force. It is possible to resolve the gravity in terms of, means resolve the gravity in terms of superposition of gravitational force of attraction on the object by the earth and centrifugal acceleration on the object arises due to rotation of the earth. You see, right, as you can, the earth is rotating about the sun is because of what? Because of force of attraction between the sun and the earth. At the same time, it should be falling into the sun, but it is not, because it is rotating about the Sun, Earth. So there is a force of attraction, the same time centrifugal force of repulsion. Okay, let me write down the force of attraction in one way. Okay, right. So force of attraction is towards, and force of repulsion is away. Not repulsion, sending something away from the rotation. So you just take a metallic ball, tie it to a rope, and try to rotate. You are trying to pull the ball towards your hand, but because of the rotation, it is rotating and it is doing a circle and is trying to go away. So those both the forces becomes equal and it exists in a rotation. So that is what happening. So it is said I can resolve the universal gravitational force or the gravity into two components. One is gravitational attraction. Okay. So another one is centrifugal acceleration on the object. Centrifugal acceleration in the sense the force with centrifugal force acting away, you divide it by mass, you get a centrifugal acceleration. You divide the gravitational force, attractive force towards the sun, you will get the you get the gravitational acceleration. Okay, right? So both of them are resolved and they define, means it's like just like a quantum state is resolved into ground state and the excited state, if you remember that. So here 0 ket stands for probably gravitational attraction, 1 ket stands for centrifugal acceleration. Okay, so that is what they were saying. As gravity depends on the time and space, one could get the valuable information on the distribution and momentum of Earth's masses with the change in this quantity. Okay, right? So obviously, objects change their masses. Okay, and they're lying on the surface of the Earth. Okay, so because of the change in the mass of an object, so they see a different state of existence. One simple fact is, for example, volcanoes. Because of volcanoes, what happens? The volcano erupts, some material erupt from the core of the earth and comes out. So there is a redistribution of masses. And because of a greenhouse effect, around the North Pole, the glaciers are melting. They're supposed to be in a solid form. They're melting and become water and redistribute. Mass gets redistributed instead of staying in one place. Okay, so these are the things which are going to change the way the gravity and acts on them. Okay, so what one can do is one can have more sensitive sensors in measuring this gravity effect, and even a small changes could be manifested from the distribution of earth masses. Okay, so even a small change of glacier melting, what would the effect of earth's gravity and the object, you can easily find from there. Okay, so basically earth gravity, you see, is dictated by mass of the earth. It's redistributed. In that case, for example, gravitational force on the moon due to earth may change because of redistribution of the material on the earth. And even there was a news some time back, how fact I don't know. So China has built a huge dam. Okay, because of that, what happened, more amount of water has accumulated in one location which is supposed to flow down. Because of that, earth mass which is supposed to be redistributed has just concentrated at one point. Because of that, they were saying earth rotation got affected by few some femtoseconds or something, like 10 to the power of minus 20 seconds or something. So that was the effect they were saying. But anyway, redistribution of the mass is going to affect the gravitational force. And if you have a powerful sensors to measure, you can get more insights about the various things can happen on the earth. Okay, so that's what they're saying. Study of the earth masses and the eventual gravity variations would lead to better understanding on glacier melting, groundwater changes, and flooding and volcanic activities. Okay. And one more thing, if you see, gravity measurements could be either based on a sensory information acquired from the satellite, or you can do the same thing by terrestrial stations which are housed at different points on the space on the Earth. Okay, so let's go further and see what could be a working principle for this measuring the gravity. Okay, so these are called a quantum gravimetry. Okay, so basically it's consisting of minerals, or you can just take a collection of rubidium atoms. Okay, so what they do first, okay, so rubidium atoms, if you just take, right, if I trap the rubidium atom in a vacuum chamber, see, atoms are like they goes here and there because of the surrounding ambient temperature. What you can do, you can fire onto them some lasers. Laser go and hit them and excite them. When the lasers, like atoms get excited, what happens is they go to some higher state. While coming down, what happens? Amount of energy they have taken, let's say 100 joules they have taken, while coming down we can ensure that they can come down to much lower state, which is by emitting something like taken 100 joules, in return they are given something 120 joules. So the 20 joules of extra energy which is there inside with them is also given in addition to 100 joules and emitted. So in that case, what happens, the energy of the system or the part in the rubidium atoms got reduced by 20 joules. This is possible because they lose the energy in terms of the temperature. So this is called laser cooling. What I mean is, okay, let's understand laser cooling. Okay, let's say, right, so electrons are, okay, somewhere here, excited state. Okay, already in the second excited state, they have some energy, which is, let's say, E1 energy they have. Now I send a photon, which is matching with the 1 and 2. I'm sorry, 1 and 2. Now electron get excited, stays there. Okay. And after some time, instead of coming back to 1, what they do? They go down all the way to lower value and they emit the photons. Okay. Wait a minute. They emit the photon. Okay. All the way, right? All the way having energy H1 2 plus H1 H omega 1. They are already existing with H omega 1 energy, and that energy also they will emit along with the photon they consume. Now what happens? The overall photon energy is much larger than what is given to them. So in this way, the internal energy of this particles got reduced. But the internal energy reducing means the temperature is going down. So this is called a laser cooling. And how do we do? You start, see, there are so many states. Okay, so many states. Initially, let's say electron is here. You shine a photon, it comes down to the next, the level much below. Again, you shine a photon, you bring it back. Again, okay, bring it back to here. Again, you shine a photon, bring it to down. So altogether, it's like a hopping. Okay, okay. So they come down all the way to absolute zero or very low temperature, which is required in the first place. Okay, so this is what laser cooling involves. Three atomic levels. Okay, laser cooling continuously I can remove. Laser cooling continuously removing energy from a system. Okay, right? So that is how you can do that. So initially the energy is removed and you put everything into one zone where the energy is almost zero. Okay, using a specialized laser beams, the atoms are cooled to microkelvin temperature. So microkelvin temperature, much lower than millikelvin temperature we all talk about in the case of cryogenics where quantum computing is being taking place. Okay, now once that is done, okay, these are cold atoms by the way, and these move very slowly because they don't have energy. If I drop them, if I slowly allow them, okay, and also the atoms are cool means they are not haphazardly moving, so we can observe them with ease for a longer time. I can observe that's very stable. Okay, so one more thing is they behave like something called matter waves. Okay, so they behave like matter waves means they propagate just like a waves propagating. Okay, so for example, if you just take a slinky, you can create a matter waves going slinky. Okay, the spring system, right? Okay, so these matter waves are there and it permits us to measure precisely the motion of the particles of the atoms using atom interferometry technique. The moment it becomes slow, you can measure them perfectly where they are located, how they are moving. Okay, now this cloud of atoms, the cold cloud of atoms, are led to free fall from the top. Okay, for sure. In a some kind of a hollow cylinder, they were led to fall atoms. Now what happens? They start falling. While falling, what you can do is you can hit them. You can hit them with a pulse of photons. Okay, if you can hit them with a pulse of photons, what happens is you can split them up. Okay, you can hit them with the pulse and split them up into a superposition of two wave packets. Okay, just like a pulse is there, pulse is made up of two signals of sinusoidal or cosine function. You can separate the two pulses into two signals. The same way, I have a clump of cold atoms which behaves like a matter waves, and I can separate them into two waves. And two waves we are going to have different propagation velocities. This is like propagation, the way they are traveling. It's like there is one group of students into one group, another group. So I can let them to go and do some work depending on uh, their depending on the way they work, their interest and all, they make it for different groups and they travel. Now, the two groups were formed and they travel down. Okay. Now, what I want to separate them. Okay. So, what I can separate is I can reduce the group velocity of one of them by just reversing their group velocity direction. Okay. I can't stop them, but immediately I can change the group velocity by how I can fire with another pulse. Okay, where is that? I can hit with the pulse that splits the each of them. So that is here. Okay, the next thing is as they pass through the midway, what we do, we, okay, the two atoms and their wave pockets are hit again with another pulse to reverse their momentum states. Means the momentum of, let's say, purple ones coming down, momentum of green one going up. By the way, I can't completely push them going up, but I can at least slow down by reversing the momentum. So the green ones comes a little bit slower than the purple ones. Okay. Once you do that, so they are like two groups are traveling together, one after the other. Towards the end, what we do, we let them fall. Okay. And I will have a pulse, a third pulse, I'll just fire onto them. Okay. Which will combine them. Okay, the purpose of combining is I want to create two different propagation vectors and then asking them to combine. So by using three set of pulses, first pulse, second and third pulse. Third pulse combines the both the of them. Okay, right? So I am just going to create two different different groups and then separate them and then put them together. On the right hand side, what you see is this. Okay, on the right hand side you have is distance versus time. Along the way, you see how the propagation vectors are changing space-time trajectories of wave packets. Okay, right? Okay, the way it is being slowed down, one of them is slowed down, one of them is speed is got increased. It just covers much quicker. Okay, you see, one of them covers a distance much quicker, other one slower. Okay, fine. Now the next level is, let's go to the next level. Okay, now what you can do is, the moment you do this, we can carry the measurement of the momentum states of the atoms at the end of the interferometer, which allows for a determination of other acceleration. What is the target I need? I want to find the acceleration, right? How they're traveling down. Okay, knowing the acceleration, I can also find what is the superposition state we are looking at. One is centrifugal force, another one is gravitational force of attraction. From there, I can get more insights about the gravity of the earth. Okay, so this is the working principle of the gravimetry. So now what this in general looks like in reality, this is a certain gravimeter at Paris Observatory. Okay, the source is given there at the bottom. If somebody wants, they can just go and check it. Okay, so for the past 3 decades, the exploration of quantum gravimetries have been undertaken. So currently, the technology is mature enough that commercial devices are now available. People can purchase, like a mechanical or a classical any gravimeters. The quantum instruments have very little required, and they can run more or lessly continuously at high rate, wherein having no moving parts promises no wear out. So whatever is given here is a quantum gravimeter based on the rubidium atoms. Okay, these quantum instruments could also include previous classical techniques, like continuous operation. Okay, right? So mainly the most important thing is these instruments are known for excellent short-term stability and accuracy up to 10 to the power of minus 8 meter per second acceleration calculations. You see our acceleration due to gravity. Okay, 1 minute. Acceleration due to gravity is, okay, g is 9.8 meter per second square. Okay, so the value of this one is accurate up to 10 to the power of minus 8 significant figure. Okay, that is a nearly 9 significant figure where accurate, that much accurate, you can find the gravity, most important, using these gravimeters. Okay, and some other solid state sensors are superconducting quantum interference device sensors. These are called squids. Okay, solid state based sensors. So in the squids, what I have here is a superconductor. There is a superconductor. Okay, between a conductor there is a superconductor. Now what you will do, some kind of a wedge kind of a structure you create, and you send a current through one direction. The current divides into I1 and I2 and goes through a superconductor and then recombine. Okay, you see, because of the superconductor, current becomes something different. I1 becomes I1 prime, and then they both I1 prime and I2 prime combine, they exit at a second order. Now, by studying this structure, you can find the field around this squid center. Okay, why? Because the superconductor, whatever I have here, okay, these are very, very, like, to have a superconductivity, anyway, I will cool the system to millikelvin. But the external field around this square, it is going to induce some changes in the system, so that the relation between I1 and I1 prime is dictated by the surrounding electric field or magnetic field. So what is the change in I1 and I prime, I1 to I prime, is directly proportional to, or some other way of proportional to the external fields. By finding the changes from I to I1 prime, I1 to I1 prime, I2 to I2 prime, you can find what is the external field strength. Okay, so that is the effect of that is the property of squid sensors. Okay, right? So I have a relation between the old current and the new current in terms of some phase. Okay, right? Some flux, right? So flux, you can just go through it. I'm not going to the details. Fine. The physics behind, like you see here. Okay. So dynamical equations describe the rate of change of the charge carriers. Okay. And talking in terms of, let's say, Cooper pairs or something like that. And phases could be derived from Schrodinger equation. Okay. Right? So, and the current is just any conventional NQ, okay, NQ, NAQE, right? So, that is the current equation, okay. The way the fluctuation of the output current is actually connected to the variation of the voltages with respect to applied flux, okay, flux quantum, right? So, this is how the squids work. Right. I have anything else here to be discussed? Yeah. Some other challenges for the quantum sensors. I think we touched when we talked about the NV centers. So NV center during NV center, if you remember, okay. Wait a minute. I'll just take that figure and explain quickly. So without any external field, NV center is simple like two-level atomic system. The moment you have external field, the ground level splits into multiple levels. Okay, in presence of the magnetic field, let's say external magnetic field, external electric magnetic field, not electric field. Okay, and once a splitting is done, the energy separation between the split levels may not be same as the old value. See here, the wavelength got decreased means the energy got increased, the frequency got increased. Okay, so when the separation got increased, the energy got increased. So I can put the electrons in any particular state. Let's say by default they exist in a particular state. If I fire with a green light, the exited if I exited or the emitted photons are of red light, means there is a presence of external field. If not, if the green light is not absorbed, I get back green light as it is, which means the external field is offset. That is how you use NV center for even measuring the magnetic field due to some human tissue, to recognize or to find the malignant part in the malignant part, the cancerous part in the human tissue at a very, very early stage. Okay, right? Okay, so what else I supposed to discuss? Any doubts? Quantum jump, yeah, that's very important. Quantum jump. Okay, so Virya Manikyamji was asking quantum tunneling and quantum jump. So let me discuss that. Okay, quantum tunneling. Okay, or you can say quantum jump also, right? Okay, then now just to understand, first of all, you better understand a particle in a box for this. Particle in a box means I just take one-dimensional particle, so one-dimensional box, x is equal to 0, x is equal to L. If I put a particle inside, we discussed several times what happens. The particle is so small. Let's say the size is 10 to the power of minus 34 kilogram, like an electron can move with the velocities close to light. So in that case, it is going to possess a wave nature. Okay, as de Broglie proposed, it is going to have wavelengths close to optical wavelengths. So because of that, what happens? The electron behaves like a wave. Okay, It behaves like a wave. Electron behaves like a wave, like a standing wave here. So actually, what is this is? It is going to be something like that. And you take absolute square, you are going to find where the electron is maximally located. Okay, let me draw it neatly. Okay, right? So this is absolute psi square. This is a psi. Okay. But now if you see it, okay, now electron is behaving like a wave, means there is some kind of a wave nature. Now forget about this potential well, sorry, potential box. Okay, let's try to understand. Let's say there is a potential well. Potential well. What is the potential well means? There is some kind of a hill on the either side of a, sorry, there is a well on the other side. We have a potential v of x is equal to 0. V of x is equal, so v of x is equal to infinity, and at this point v of x is 0. Means if I place something inside a well, to go to the other side, let's say it has to cross, let's say x is equal to 0, x is equal to L. Let's say an object to cross either x is equal to 0 boundary or x is equal to 1 boundary, it needs to achieve a potential of infinite value so that it can go to the other side. Means infinite potential means it's like a hill going all the way to the infinite. So I can't climb the hill at all. Okay. So there is no end for the hill. I can't climb. I have to stay within the hill, before the hill. So there is a hill is extended to infinity on the other side. That is what infinite well means. So even what you can do, okay, you can even remove this part. Okay. So this is infinite potential, right? Now what happens? I have something like this. In this case, what is the state of the electron if I ask? Okay. Now, electron state is just like particle in a box. We usually think that it is appears like a wave. Okay, fine. Okay, that's fine. Now, what I will do is I'll just take a step potential. Instead of taking an infinite potential, well, let me just take a step potential. It's something like V is higher than 0 at this position. Let's say x is equal to L. V is higher than 0. X is equal to L or less than L, I have V is equal to 0. So now I'll send an electron with the energy some E. Okay, right? So now the question is the incoming photon energy is more than this V value or less than V value is the question. Okay, usual thing we understand is, okay, if the electron energy En is less than V potential, okay, V potential, what do we think? So nobody can climb up because the energy is very low. So we think that this guy can never able to cross over to that the hill part, the step part. Okay, and because of that, even though electron has a wave nature, so it hits back and comes back and creates a standing wave pattern. That was the understanding. But the thing is, even though energy is less than wave, if you try to see the wave presence of this electron, if I find the solution from the Schrodinger equation, what I see is wave is going and hitting this part. Okay, let me draw it neatly. Waving hitting that. Okay, it goes and hits it. Like where the energy of the electron is less than V also in this location. Okay, so even in that location, wave is not going 0. It is exists some value and then decrease. Okay, what is basically happening is even the electron wave is present inside, even present inside a potential energy which is much more larger than its existing energy. Okay, it's like even the electron doesn't have energy to cross over to the other side, but still its wave nature is going to exist on the other side. Let's say there is a wall. Okay, when you speak, our sound travels, penetrates to the wall. It's like a wave. Okay, the same, the electron wave always even goes inside this potential. Okay, larger energy. And now you take absolute square of this one. Okay, you would see a maximum presence, maximum presence, maximum presence. Okay, so even electron presence is there at some point inside this potential. So this is called tunneling through, or punching through some location where even though electron energy is much lower, still it is able to go into that material. So this is called tunneling. This is possible only because electrons behaves like a waves. Okay. Okay. So let me see. There is a very long question here by Sai Kumar ji. Regarding the gravimetry part, I have a doubt. In Schrodinger equation, we consider mass to be point mass or localized, while we consider a charge to be distributed in space. When we consider a eigenstates, we consider a charge to be distributed and the and forms s orbit, p orbit in hydrogen atom. Example. Okay, for example. Similarly, we assume if multiply probability density by charge, we get a charge density. Okay, even for hydrogen atom, we does these things. It is like inherently we assume charge to be distributed while mass is localized. Is it possible to do some quantum mechanics by assuming mass to distributed? They may have some minor role macroscopic or mesoscopic objects. Mass being distributed at 2 points in superposition of a superposition of space eigenstates would be related to gravitational effects or quantum objects, right, sir? Okay. The question is, in the case of hydrogen atom, okay, please remember the charge is not distributed in space. Okay, right? So the probability of existence of a charge is distributed. What I mean is, for example, hydrogen nucleus is there. I'm just trying to draw. I'm just trying to draw in 2D, the hydrogen atom would look like there is a first ground state orbit. Okay, the electron is there. Because of the electron is so tiny, its wave nature is shown on the orbit. Okay, something like that. Now, if I take an absolute square of this wave nature, you would see the presence of the electron, okay, maximum at some location. Okay, so basically what you are going to do, you are going to draw about the nucleus possible locations of, maximum possible locations of electrons. Okay, it doesn't mean everywhere the point which I have shown is an electron. It's no, it's a probability distribution. The electron may exist here, also exist here. So basically the electron distribution in this probability is distributed around. Okay, so I cannot say, right? I cannot say the mass can be distributed here. No. The electron mass would exist at one point only. Okay. How should I know? When I go and catch the mass electron, it falls to one location. It is just like if I have a vibrating tuning fork, if there's a hit the tuning fork, it is vibrating. Okay, so while hitting a tuning fork, vibrations are there. If you touch the top vibrating part, it suddenly drops to a no vibration state. So that is what the electron presence is possible in every location because of its probability distribution. When I try to catch it, what happens? It drops down to one of the location. Probably it will drop down to one of the location. The moment I catch it, it's no more rotating about the nucleus. It's as if I have just taken out of the atom. So that is what happens. But when it comes to applying a superposition, instead of applying a superposition for mass distribution, what you can do, you can try put a superposition for something called matter and antimatter. Okay, so dark matter people call. When it comes to astronomical physics or higher energy physics, people use antimatter and matter. So for every matter there is an antimatter people call. So there is a connection there. Probably you can try from that prospect. Okay, right? Have I answered your question? So orbital distribution, s orbit, p orbit, d orbit, f orbit, these are all simply the way the electron presence probability distribution is distributed around. So there is a orbital structure like this. There is a circular orbit structure like this. There is a orbit structure like this. These are all the probability distribution around the nucleus. This is the orbital distribution. Okay. So that is what we see. But there the mass is not distributed. Please remember, it is a probability is distributed. At a given point, if I try to catch the electron, the entire probability is gone, entire concept of probability is gone, entire concept of quantumness is gone, entire concept of duality or wave particle duality is gone. System becomes classical, deterministic system like a material. Okay, fine. Okay, so any other questions? Yeah, if needed, I think we can discuss one-to-one Sai Kumarji. So very good question. So please explore in terms of matter and antimatter. So in the case of gravity, you see the gravitational force is resolved into two components. One component is accelerate the gravity, gravitational acceleration. Another one is centrifugal force. In the same context, you can think. Okay. Right. There is a question by Bhavna ji. How do we define gravity with respect to photon? Uh, yeah, I am not sure. So, yes, when it comes to like say black holes, even light can't escape. Okay, right? Okay. Okay. So in terms of mass, no mass. Okay. Yeah, it's a very good question. Puzzling question need to be answered since mass is not there for photons, and people do say in the case of in the black holes, light even can't escape. That high level gravity is there, which means even though photons have doesn't have a mass, still attracted by some gravity. Okay, right? See, you say sun emits the light, it is not attracted by the earth, it is just propagating in every direction. Earth happened to be in one of the direction, that's why we are getting the light. It doesn't mean we earth is attracting the light, so that is what we are getting. It's not that. So photons are not attracted, they're just propagating. But when it comes to feeling the magnetic uh, gravitational force, photons do feel gravitational force when the object, not object, some infinite gravitational pull is there somewhere, like a black hole, though even photons get pulled towards it. Okay, maybe from that context we should think, but as of now, I don't have an answer. So, how can I have a gravitational pull on a photon? I don't see straight away. There is no gravitational effect on the photon as such. Okay, but in theory, I can have momentum, and even I can measure the momentum of a photon, even though it doesn't have a mass. How do I measure a momentum of a photon? Simply hit a photons to a very tiny objects. I see how much momentum the object has achieved, how much recoiling momentum the photon has. I see there is a reduction in the momentum of the photon. I see there is a acquisition of momentum in the case of an object which the photon has hit. From there, I can associate a momentum to the photon. So that is what usually we do, but we don't talk in terms of mass of a photon. You can even get exactly what is the associated or corresponding mass for a photon. The calculations are there. Okay. Right. There is a one more question quickly. I'll just go through. What will happen if we bring real physical magnet inside quanta phenomena in terms of phase or electric field or energy changes? That is what we are seeing, right? In the case of squids, you mean, okay, you get back here. See, even what is this? NV center diamond. See, NV center is there inside a diamond. I bring external magnet. It is going to affect the way that NV center respond to the external field. How much change is there depending on I will get the magnetic field strength of the external field. Okay, so that is the one way of finding the external field strength. Other one is the gravimetry. What is the changes in the earth gravity? Earth as a bar magnet. Squids. So the squids are actually measuring the external magnetic field. So basically, you have a squid setup. You are bringing external magnetic field source and measuring what is the strength of the source. So when you bring a very powerful magnet, probably it disturbs the entire state of a small distribution of quantum systems. If it is minute enough, it induces small changes in the uh, any equipment which we choose. Okay, so the gravity would affect the frequency. When it comes to the light, probably you're saying the light frequency gets affected. Is it a question or a statement? I don't know, Professor Bibaji. Does, if I ask myself, does gravity affect the frequency of light? Okay, straight away as of now, just a comment. Okay, you mean to say gravity would affect or not affect the frequency of light? Okay, you can comment it. Okay, so it's already 407. We'll stop at this point. Yeah, it would affect. Yeah, thank you. Right, we need to find out. Okay, so it's interesting thing. We need to find out. Okay, fine. So I'll stop at this point. Thank you so much for all the participants throughout my sessions. There were very interesting questions. Okay, so I noted here and there like questions for today also. I'll note it. I check it somewhere sometime and I'll find out the answers. If you find some time, you can get in touch with me and we can discuss in person. I would be happy to take your calls. And so once again, I would like to thank and sincerely express my gratitude to Avasti sir, Manoj sir, for giving me the opportunity for taking this many number of sessions for you people. So I have developed a lot of codes, so that is a plus for me. Okay, so I got a very good exercise of teaching, like discussing things, and I got to know where to stress, where to not to stress, which points to elaborate, now which points to not elaborate in a another better understanding way. So thank you once again, and a few more sessions to coming around. Okay, I think tomorrow and after tomorrow. Best of luck for those things. Yeah, gravitational redshift, gravitational blue shift. Yeah, the redshift and blue shift happens. You know what? You know why? The stars are receding away from us. The light which is reflecting from their surface. See, when the star is close to us, it reflects the light. When it is away from us, it reflects the light. As it goes away, the wavelength increases, reflected light. Wavelength increases means the energy, the frequency decreases. This frequency decreasing is actually called a redshift. That's why the receding stars start going away. Okay, their energy would appear for us the lower energy, very faint, which means they're going away. So intense image I see. Okay, it is just opposite to redshift. So the redshift and blue shift happens because of star motion going away and close. Okay, yeah, in a way you can connect the gravity. Okay, gravity, but actually the entire solar system is spreading, galaxy is spreading. Because of that, stars are going away from us. That is what we see redshift. Okay, right. Thank you, Rao sir. VC Rao sir, VCV Rao sir, for a nice comment. Okay, then I would thank all the participants for your kind comments and interesting question. How many students are working with you in quantum? Virimanikyamji. Yeah, I have okay. Recording is there. I think I request Avasthi sirs to just stop the recording. We can do general discussion.
Okay, thank you, sir. So I request my staff to stop the recording because we are come to the end of today's lecture.
Mm.
And once again, thank
Yeah.
you, Aswa sir, for your wonderful time and patiently answering all the questions, all the queries of the participants. So it
Thank
makes
you.
more interactive course. It would be better like we are because if you are teaching in a classroom, you can see their face, you can visualize their expression, you can understand.